All right, so today we're going to talk about solving some harder trig equations. In particular, these examples are going to be requiring factoring and simplifying using some of those trig identities that we learned. So not only are we going to be adding, subtracting, multiplying, dividing on both sides, we also might have to factor. We also might have to use some substitution with those trig identities that we have. So I'm going to point out a couple of things, but I suggest that you go back through and replay um, after you write all of this down to kind of think about what's happening. But basically, in this first example, you'll notice that I have all of the same function. They're all sine functions, which is great. And then in those sine functions, we have a squared and a linear term. So a squared, sine squared, and a sine to the first power. So that kind of signals to me that maybe this is going to be quadratic. With quadratics, the first thing you want to do is get it equal to 0. You can't do quadratic formula or factor without it being equal to 0 or take the square root, but in this case, we're not going to take the square root. So once I get it equal to 0 by subtracting 1, then I did quadratic formula. Quadratic formula gave me two values. That's what quadratic formula always does. It gives you two values. Those two values then are equal to the sine of x because that's what's being squared, or that's what our linear term is, the sine of x. So if I go through and find each of those two values and set them equal to the sine x, then the problem becomes like it was the other day when we did basic solving trig equations, where we have to get the x by itself. How do we get the x by itself? We take the inverse. So I do that on both equations or both sides, and I get the inverse of negative 1.78 is no solution. The inverse of negative 0.28 is negative 0.28. From there, it's just like yesterday, find the second solution using that 1/2 the period minus the first solution. All right, taking a look at our second one, this one's a little more complicated because if you look at the second example, the first thing you notice is that one is sine and one is cosine. That's a really big problem. We cannot do it if they're two different trig functions. So what do I know about cosine? Well, I know I can change cosine to sine using that Pythagorean identity. So the first thing I did was go through and get the constant on the other side, right? That's number one, the first thing, so that it's equal to 0. And then I'm going to replace that cosine squared with the 1 minus sine squared. Go through, if I replace it, then I have to distribute that negative. I will combine like terms. And when I do all of that, you'll see right here, I have another quadratic, sine squared, sine x, and then a constant that's like this kind of quadratic. Instead of doing quadratic formula, because my coefficient is 1 in front of my squared term, then I'm just going to factor that. So I get the sine of x plus 2, the sine of x minus 1. And when we have a factored solution, then we're going to set each of those factors or parentheses equal to 0. And that's how I get my solutions instead of doing quadratic formula like in the last one. You certainly could do quadratic formula if you want to. You do not have to factor it. It's just kind of if you can see that quadratic or not. Solve each of those solutions then for the x value by taking the inverse. Again, we get one that's no solution. And the second one, we get that our value is pi over 2. You're going to want to use your unit circle for that. If you go through and find the pi over 2, you might want to find your second solution down here. But when you've plugged that into finding our second solution, like we did the other day, you'll find that pi over 2 is the value that we already had. It's the same solution, the second solution, etc. So the problem is I can't have two solutions that are exactly the same thing. I need another solution. And if you go back up, you'll see that our values have increased from 0 to negative 2 pi. So we have a larger range there. And if I wanted, then I could take my pi over 2 and I could go backwards one period. So find that other point on another sine curve back one, and that would give me another value. So I do that here in the green. You'll find your pi over 2, subtract the period, and that gives you another point farther back on another sine curve, and that gives you negative 3 pi over 2. So there's my two solutions. Now, For 9, we're going to go through and find all the general solutions. Remember, general solutions are where you add in your period times n to tell about all of the solutions you could have all the way to the right or positively and all the way to the left or negatively. N stands for any integer. So anytime you want to find a different value, you would plug in that any integer. This one's going to be a little similar to the one we just did previously, where we have one cosine and one sine squared. So I need those to be the same trig function. So I'm going to use that Pythagorean identity. Of course, first I set everything equal to 0 because I can't do quadratic formula or factoring or anything like that if it's not equal to 0. Then I replace my sine squared, so I have all the same trig identity or trig function in cosine using that Pythagorean identity. Distribute my 2, that gives me a quadratic. Notice this quadratic has a coefficient, right here, of 2. So I'm going to do quadratic formula for that because I don't feel like factoring something with an a value. If I do quadratic formula, I get the values of 0.62 and negative 2.73. Now, previously, one of our solutions was no solution. So in this case, we have we have a solution for this one and a no solution for the negative 2.73. So only the 0.9 is what we're going to go with, and then use that to find our second solution. Remember, with cosine, you're just doing the period minus the first solution, not both, or not 1/2 the period because of the cosine symmetry. So 2 pi minus 0.9 gives me 5.38. And then when I write my general solutions, it's the first solution plus 2 pi n, and then the second solution plus 2 pi n, or whatever your period is, n. All right. So with number 10, you might notice that there are two trig functions again, tangent and cosine, but there is a tangent in both of them. So that kind of sets off the alarm like, maybe those are both a common factor. So indeed, that's what I ended up doing, is taking out that tangent x as my greatest common factor. And then that leaves just all of those numbers and the cosine within the parentheses. That's great news because now I can set each of those factors, the tangent of x, and then all of this stuff in parentheses, equal to 0. So tangent of x equals 0, and then all the stuff in parentheses equal to 0. Tangent of x is easy. I go through, take the inverse, find it on the unit circle. Over here, it's a bit more complicated. I have to add 1 and then divide by radical 2, and then I rationalized it. So if you're wondering where this radical 2 over 2 came from, I divided 1 by radical 2 and then rationalized that. Again, I'm going to use my unit circle to find the inverse, and that gives me pi over 4. So now I have two solutions, 0 and pi over 4. And for both of those solutions, I have to find a second solution. So I'm going to have 4 total answers for this problem. 0, and then take my period and add the second solution. And then over here, pi over 4, and take my 2 pi and subtract pi over 4 here. Remember, the tangent function second solution is a little different from that. So there's all your answers in that second or fourth solution for number 10. All right, for 11, this is our second to last problem here, friends. I am happy that I have a sign for both of those functions, which is great, but this is our first double angle identity, so you'll see that 2x inside the parentheses there. So we're going to go through and we're going to replace that with our double angle identity, and that's going to introduce a new trig function, the cosine. But lucky us, we still have two sines, one in the first and then one in the second group. So that tells me again its greatest common factor. So I factor out my sine x, go through, set equal to 0, both the stuff in parentheses and the sine x equal to 0. Use my unit circle to find those first solutions, and then use the formulas for sine, and then over here for cosine to find those second solutions. Don't forget we want all the solutions, so over here you'll see in my answers I have 2 pi n attached to each of those solutions. Also, you can tell in this problem there wasn't a range given, so that means they probably wanted all the possible solutions, including the 2 pi or the period n values. All right, last one. when we talk about this one, again, we have double angle and we have cosine. So I'm going to replace first my double angle with our cosine. And remember, if you look on your sheet for cosine double angle identities, there's actually 3 identities that you could pick there. We want to pick the one that says 2 cosine squared minus 1 because that will keep everything still cosine. If you pick some of those other double angle identities for cosine of 2x, then you're going to get other trig functions, and you don't want other trig functions. We want to try to keep it all the same trig function as possible. So I go ahead and replace my 2 cosine squared minus 1. Go ahead and put that in quadratic formula version. So squared term, linear term, constant. Use your quadratic formula, get your values of 1 and negative 1/2. I would use my unit circle for each of those. So I'm going to get 0 and 2 pi over 3 when I take my inverses on my unit circle. And then go through and use your period minus the first solution for both to find your second solutions. So really that gives us 4 numbers, 0, 2 pi over 3, 2 pi, and 4 pi over 3. But when you look, the question asks for the interval between 0 and 2 pi, where 0 is included, but 2 pi is not included. So that means that my actual solutions are 0, 2 pi over 3, and 4 pi over 3, and 2 pi is not included in that interval. So that's solving some equations with factoring. It does require you to know a little bit about quadratics and to think about those trig identities some more. So if you're not familiar with those, you definitely want to pay attention to them. If you have any questions, please see me during office hours.